Okay, so everyone online, we're having a discussion here. I watched one of the videos and realized that I'm not being very good about repeating questions from the audience and stuff like that. So what we're doing is we're having a very important discussion here about whether one, if you are a ring, is one in the ring. And the answer is yes, it is, but apparently there's also an RNG, which is a ring without a one, or maybe potentially without a one. I'm not really sure, and I actually don't really care a whole lot. So anyway, so today we're going to do more of the sheaf cohomology stuff, but today we're going to do Cazot complexes. I realize that I feel a little hamstrung because a lot of you don't know them and I can't just use them. So it's really important to say something about them. And meanwhile, after we do this, we'll actually define the maps in a check complex also. So the maps in a check complex. This contains a little bit more. We have to do a little exterior power stuff. And then we're going to do the theorems of Serre on sheaf cohomology. And then we're going to do the Hodge diamond. Oh, no, sorry. We have one more thing to do before that. Yeah. The omega 1 on X, the sheaf of one forms. Well, and we'll already have also doing omega p of X. That'll be the sheaf of p forms. Okay. Once we have a module that gives us this, it's pretty easy to get that, as we'll see in this whole thing. And then we're going to do the Hodge diamond. We probably won't quite do all this today, but I'm hoping we do. And the real goal in some ways is the Hodge diamond command in Macaulay 2 is really bad. And well, it's correct, but it's not efficient. So being able to think about what you want to compute in such a thing is going to be one of the goals, and see how little we can get away with of that. First, though, I wanted to mention that I have made a GitHub a Git repository called I think this is the name of it. I hope it is. If someone can check it. In here, I have the week 6 PDF file for some problems to work on, and I have 2 different Jupyter notebooks with their PDF files, so that you don't have to actually recreate them. They're drafts, okay? Because I'm still learning all this stuff, and I'm hoping to get hints from you. For instance, I could not figure out how to put more title information on it on the PDFs. And anyway, so they are on Cazot complexes and checks, and this stuff here. This part's not in it yet. And then the other one is on computing this stuff here. So so those would be good things to do during the project portion of the time. I also am hoping that for people, especially people taking the class, but anyone, that I would like to add more Jupyter notebooks for different things. Keep them pretty short for each thing, and have ways of doing it and collect them in here. And I think that would be a great thing for people to do. At the moment, you would have to have. I will have to explain how to get Jupyter on. I think I sort of did last time, but nonetheless, I think this would be a really good thing to do, and I would like to keep improving the ones that are there already. Okay.
So I created a gist. You can have a short little description.
Yep.
Gist, which says
Okay, yeah, that's right. So Arthur created a gist on GitHub that explains how to get Macaulay 2. No, sorry, not get Macaulay 2. To get Jupyter set up.
it would get installed as an engine, and also to turn off sort of like the input line wrapping.
And also, it turns off the output line wrapping, which is kind of important. With the newest version of Macaulay 2, you can get tech output also, or some sort of something, it's math ML, but it looks like tech. And but that's not in the released version yet. That there's a bug in that, and so it's only in the current development branch that gives you that.
So where on the GitHub is the gets?
That's a good question. We'll have to we'll figure it out and get it on here in the project section. Yeah, I have it written down.
Okay, so in the GitHub repo, you should have a README file. So you could put the link to the gist of the.
That's right. Okay, we will do that. So what was suggested is there's a gist for doing the installation of Jupyter, and we will put a link to it inside of the README in this repository. Okay, if you don't know how to get at these kinds of things or whatever, we'll write down the exact link. You actually do not really need to clone it on your own computer and everything, although it's a good idea, but you can just look at it from there. I also have for the ones today, I have printouts of the stuff here, so that during the project time we can do some of that stuff. Okay, enough of that kind of stuff. Let's get going with the material of the day. Okay, so so first thing we want to do is Kazoo complexes. But even before doing that, we need to do first is recall the exterior powers. So recall wedge P of F. Okay, so here's the situation. This works for any ring. R is equal to a ring, potentially a ring potentially graded. So commutative ring with identity, right? Okay, so this is what this is. It's our usual thing. I oftentimes think of it as Noetherian, but this is pretty general situation. And F is equal to a free module. And let's say that generated by E1 up to M. Okay, so it's equal to the direct sum of R times E sub I equals 1 to M. Okay, if R is graded, and the E sub I are, and F is 2, let's set the degree of each EI is equal to D sub I. Okay, so then in this case, F would equal direct sum of R twisted by minus D sub I equals 1 to M, because of the nasty chain, the fact that we have to use negative there in order to get the degree DI generator. Okay, so this is, we're oftentimes going to be using this. In fact, we're almost always going to be using this in the case where this R is a polynomial ring, just the straight polynomial ring, and this will be a free module inside of there. Okay, now that's fine, but so now what is it? So recall that if I have a free module, it's like vector spaces. If I have a free module, I can calculate what the exterior power is. So recall that wedge P of F. Do you all know what the exterior powers of things are? Well, in this case, you can think of it as following. This is equal to the free R module generated by subsets of P of the generators, essentially. So generated by E, let's see, do I actually want to give it, I will say EI sub 1 wedge EI sub 2 wedge, you can think of these as symbols in some wedge I sub P, where I1 is, say, between 1 and then these are in order, IP, and that's less than or equal to the number of things in F, which is M. Okay, so you can think of it as this. So basically, it's got one generator for every subset of P things inside of here. So the rank of this free module is equal to P choose, M choose P. Okay, that's how many subsets there are of those. Okay. If F is graded, like above, then so is wedge P of F. And the degree of EI1 wedge wedge EIP is just equal to the sum of J equals 1 to P of the degree of each E sub I sub J. Okay, so it's just when you multiply things together, the degrees add. That's all it is. Now, if you're not familiar with this notation, one way to define this is to take the P tensor product power of this. So F tensor tensor F P times, and then you mod out by something that makes it skew commutative. So here we also have that we can use any elements wedged here, but we get that EI wedge EJ is equal to minus EJ wedge EI. So if I flip around any two elements in here, it negates it. It's just like from differential geometry and things like that. So we have this, and we also have that EI wedge EI is equal to 0. Okay. So this you have to say in characteristic 2. I don't think it completely follows otherwise. So this is the module of essentially P forms on F. Okay. What are some features of this? So for an example, how about if I take wedge 2 of r to the 4? So this is F here, is r to the 4, and it's generated by, so F is generated by E1 to E4, and wedge 2 of F is now generated by all things of two things. So here is a real problem though. E1 wedge E3, what order do we put these in? In Macaulay 2, for instance, and everything's ordered. So you need it somewhere to figure out what that is. One of the Jupyter notebooks sort of gives a way of figuring that out without looking at documentation. But in fact, this is the order it will use. It goes up. I don't know if this is not lexicographically. E1 wedge E4. But anyway, this is what it is. Wedge E2 wedge E3. 1, 2, 1, 3, 2, 3. We have to do all with 4 now. So E1 wedge E4, E2 wedge E4, and E3 wedge E4. So this is equal to 1, 2, 3, 4, 5, 6. This is r to the 6th. Like this, okay? So you could do this for an arbitrary module as well. But then you have to really go back and think about the definition of it. So this is, for the moment, before we do Cazaux complex, let's just do this here. So suppose that M is an R module with presentation okay, I'm going to do it like this side today, just to sort of keep you on your toes. Okay, and in part because it matches the other thing. But here is it's going to be F and G. So this is R to some power, and this is R to some power. They might be graded free modules if M is graded. Okay, and let's call this matrix phi. Okay, then so notice that if this is R to the A and this is R to the B, M is generated by A elements, the images of the E1 up to EA here, right? So in some ways, if you think about it, the wedge P of this is going to have to be generated by the images of all the P wedges of those things. So let me write this over here. then proposition, which we will not prove, is the following, that wedge P of M has a presentation on the Jupyter notebook. The first part of the exercise, besides proving this.
Sorry,
is
can
that
we
it's
switch the
fine.
camera?
Oh, yep, thank you. Okay, so I'm looking at this, wedge P of M has a presentation. The first part of the exercise is to go back and make sure you remember what the definition of wedge P of M is as a quotient module, okay? But here, it's just going to be the following. Oops, I don't have it here. Where is it? Oh yeah, here it is. Has a presentation, and it's going to be wedge P of M. And it's generated by the images of wedge P of F. Okay, so that's what I just said. So if I take any subset of P things of the generators here, that will be generating wedge P of F. Now, when is an element 0? When is a element of wedges of these things going to 0 here? In other words, it'll be we need to map to it. If any element of those things is in M, then even just one of them is in M, it's 0. Okay, so then it turns out that what you can do is you can do the following. Which order do I want to do it in? It doesn't really matter. Do it this way: wedge P minus 1 of F, tensor over R of G. This is a very nice free module here. It's just given by the rank of this times the rank of this. So, and this is essentially, you take a P minus first power, you do this, and you just wedge them all together, and that will go to 0 here. So their exercise, which is mentioned, is define this wedge P of M carefully. That's 1. 2, show what this map is here. Let's call it psi. Define psi. Maybe on a specific example even. Yes, question? No? This is phi. I can't use wedge P of for that because that's not what this map is. It's just some related map. Yeah, sorry, it's a little my phi's are ver phi's in fact. Yes.
Okay, so when you're defining power, you've already said that the indices have to be in a certain order. So like these rules really only applies if you're defining the product over all the.
No, not necessarily. I could take, I can say inside of wedge 2 of F, I could take E1 plus E2 wedge E3 plus E4, for instance. And then and because it's
Whereas up here,
that's true. I'm assuming that you know this is a product on the exterior algebra.
right, so
And I'm sort of was trying to avoid going through to the whole exterior algebra here, but maybe that was a mistake.
yeah, I mean
Actually, it probably is a mistake. I probably should have just defined the whole exterior algebra and then said this is the degree P part of it, you know, that has those things. But the point is here it's linear in these free modules or in wedge P of M. This thing is equal to E1 wedge E3 plus no. Let me do this in a different order here. Let's do E1 plus E3 wedge E2 plus E4. This is E1 wedge E2 plus E1 wedge E4 plus E3 wedge E2 plus E3 wedge E4. And I guess the only one that is not in the form there is this one. So in terms of that basis, this element inside of this in this free module is equal to E1 wedge E2 plus E1 wedge E4 minus E2 wedge E3 plus E3 wedge E4. But maybe I should have just defined the entire exterior algebra first. Yeah, right. So here, this is wedging this thing with, not with well, the map here should be something where you you take phi of this guy here, that gives you an element of F, and then you wedge the element there with it. And it doesn't really matter, you have to just be a little careful about signs, but anyway, define this, and 3, prove star. Okay. But it is true, I probably should have done it in terms of the entire exterior algebra. Maybe I'll change the Jupyter notebook to do that. Okay, so anyway, we're not going to do this much, but there is something to learn from this. We're going to be using this to get the sheaf of P forms. Once we have the sheaf of 1 forms, we're going to just take wedge P of that module. But the trouble is that this could be a pretty nasty presentation, and it's still, I think, it's an open problem to, is there an easy way to get nice presentations? There are ways of getting nicer presentations, theoretically, but I don't know, is there a way that you can just do it without a big computation is a harder question. Okay, so anyway, these are exterior powers. Maybe I should define while we're at it. No, I don't have it prepared. So we should probably define the entire exterior algebra, but I don't want to mess it up.
There's a question online.
Yes. Question?
Oh yeah. Could I ask what the map between the generators and relations is called there? I just can't see it.
I just called it psi.
Okay. And what's the map between G and F in?
This is phi.
This is also phi. Okay.
No, it's different. Phi and psi. They're different maps. Okay.
Thanks.
Maybe I should call them F and G. But in any case, that is a point with the recording. Okay, so these things just get used all over the place. In particular, we're going to use it now for the Cazul complex. So we're going to let F1 to Fm be any elements in R that we like. And we're going to let F equal the free module on that number of elements. So, and then we're going to consider, maybe this is bad, I'm using F is going to be the map from F to R, which is the matrix F1 to Fm. Okay. If R is graded, and the Fi are 2, or are homogeneous, we set F to equal the direct sum of R to the minus degree of Fi, I equals 1 to M. And then in that case, this is graded of degree 0. Okay. But this is, and we'll always be using it, at least in this class, we'll almost always be using it for homogeneous things. So, so there's that. And now the definition, do I want more space than this? Definition, the Cazul complex K of F1 to Fm is the R complex, in other words, the complex of R modules, that looks like the following: 0, R, F, wedge 2 of F, dot, 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 all the way up to wedge M of F, which is equal to R, or some twist of R, if it's not that, okay? So this K is this thing here, but now I have to tell you what the maps are. First of all, let's name them. This is going to be del 1, this is del 2, up to del M, okay? So they always are named starting at the source of it. Okay. Now let's go over here. If you could change the camera. Okay, so what are the maps? Del P is going to be the map from wedge P of F to wedge P minus 1 of F. So notice it's going down here. So it goes from one thing to the next lower one. And what is the definition? I have to tell you where a free basis element here goes to. That's one way I can do it. I'm going to say EI1 wedge E sub IP, and that goes to the summation from J equals 1 to P of minus 1 to either J or J plus 1 or J minus 1. Well, J plus 1, J minus 1 are the same. I'm doing it this way, so the very first term has a positive on it. Doesn't really matter a whole lot. And then I'm doing F sub ij. So that's the one of my generators, and then I'm removing it from the wedge power. EI1 wedge EI j, leave that out, and go to EI sub E. Okay. And if you think about it, this makes sense. If I move this EIJ to the front right here, I'm going to get a minus 1 to some power like this. And then I'm mapping it via the map where EIJ, I'm mapping it using F. So this is one way to define this. Okay. Now, so the exercise in the Jupyter notebook is to write this out for the first few cases. I mean, it's all very well and nice. This is great formula, but if you don't, you got to see it also in order to really get a feel for what it's like. So in fact, let's do that right now for 3. So for m equals 3, okay, what is this? The Koszul complex on F1, F2, and F3. Well, it's going to be of the following form. It's going to be R. There are 3 generators. Then it's going to go to wedge 2 of R3, which is also R3. And it's going to go to wedge 3 of R3, which is R. So we have to figure out what all these maps are. First map we know, actually, is that true? If I take P equal to 1, what's happening? Then this thing will go completely away. All the signs will be all positive, and so I'm going to get F1, F2, and F3 is this map here. So the definition matches the 3 things that we had up there. So this is del 1, del 2, and del 3. So what is del 2? So delta 2 is going to be from R3 to wedge 2 of R3, which is R3. And now, in order to do the matrix of it, I'm going to do what I do in my linear algebra class. I'm going to write it down, and then I'm going to say what my basis is of the source space, and what my space is. I have this wrong. This is the wrong direction. This is wedge 2 of R3, which is R3, mapping to the original R3. Okay. When I do one map, it's very hard for me not to do it going this way, which is maybe bad. But anyway, so here, what are the generators here? There's E1 wedge E2, E1 wedge E3, and E2 wedge E3. And then over here, they're going to go to E1, E2, and E3. So what's the first column go to? E1 wedge E2. So it's going to be so basically, I loop through up there at j equals 1, I'm getting rid of E1. So, and I'm left with E2, but I have I have an F1 here, and I guess that's a positive sign. And then I have when I get rid of E2, I get an F2, but in the E1 spot, and it's a minus. Okay. And then the next one is, so I think it's also going to be an F1, 0, and minus F3, because not much else has changed from that. I think I've got the signs right. I have a 50% chance of getting each sign right, which is bad, because then the chance of not having any answer is having them all correct is very vanishingly small. But at any rate, I think that this one might actually be okay. So this is which one? F3 and F2, and I believe this is the sign, okay, as I've defined it. You'll find, though, in different books that it could be defined slightly differently with it up to a sign. So that just to make your life harder as far as whether you get it correct or not, you have to have the definition around. Yes?
Sorry, I was a bit slow when we were defining how the delta maps are working, or the del maps are working. So the hat above the EIJ is what?
Oh, sorry. Let me actually say that. So the question is what was the what does the hat mean? So this is a sort of standard kind of thing. This means leave this term out. So this is the product of all the other EI1 up to EIJ minus 1, wedge EIJ plus 1, and on. So you just leave it out. But it's really annoying to write that. So this is so what we tend to do instead. Any other questions? By the way, notice one thing, that each one of these things are the trivial syzygies on F1, F2, and F3, which is not a mistake or a coincidence. Well, maybe it's a coincidence, but it's but these days that's the whole point of this, is that this is giving us the entire trivial syzygies on the F1, F2, and F3. There could be more, hard to say. Anyway, that's that. What's delta 3, by the way? This is going to be from wedge 3 of R3 to wedge 2 of R3. And again, we have to do this. So this is going to be E1 wedge E2 wedge E3. And then here's E1 wedge E2, E1 wedge E3, and E2 wedge E3. And clearly we can change bases and get something similar. But anyway, so what are these things here? This is F3 minus F2 and then F1, which, by the way, is the obvious syzygy on these three things. If I take F3 times the first column minus F2 times this, those cancel, and then plus F1 cancels with both of those terms. Okay. So in fact, the exercise is show that K of F1 to Fm is a complex. Okay, if you've seen this before, you've done this. But if you haven't, you got to do it once, okay? And just see it. This is just straight algebraic topology land. So where everything, all these things are designed so that the signs on doing it twice in a row gives you 0. Question?
Simpler, you do the exterior algebra first, and you show like.
Yeah, I know, but I don't want to do it that way. So the question is, it's simpler if I do the exterior algebra first, and then I just say this is the exterior algebra with it has a differential structure on it, and I'm just writing that down. That is a good way to do it, but I would rather. I want you to see this exact this thing here. Okay, that might have been a good way to do it though. Okay, so anyway, so show that it's a complex. Is it exact? Well, actually, that's not correct. It's sometimes it sometimes is, sometimes it isn't. But in fact, when it's exact is a very important kind of situation. So I want to write that down because I'm going to write down two theorems here. Oh, right. I have to actually do. I don't know if you all did the one of the problems I gave you on the definition of depth. But let me actually write that down. So definition, F1 to Fm, these are a sequence of elements in R, so Fi in R, is a regular R sequence. I think in the book I did a regular M sequence, but I'm just going to do the ring case here. It's a regular R sequence if the following holds. If A, first of all, the ideal generated by all these guys had better not be everything. 1, which is R, okay? So you can't have the unit, you can't be able to get the identity from there. Okay. The second thing is that if I take the map, I can think of the map F1 as a map from R to R. Okay, it's just multiplication by F1. Is that okay? So this is injective. Alternatively, i.e., that just means that F1 is a non-zero divisor, NZD, non-zero divisor on R. Okay, so in other words, if I take F1, I can't multiply by something else to get 0. That's what it means to be injective. Then F2 also, I can take R now, R mod F1 and map it to R mod F1. Okay, so I just take the ring R mod F1 or the module R mod F1. It doesn't really matter what you think of it as. And then you multiply by, this is multiplication by F2. And this is injective as well. So it's kind of like non-zero divisors on steroids. Okay, so instead of just a non-zero divisor, one of them, a whole sequence of them is a non-zero divisor, then a non-zero divisor when you mod out by the first guy, and so on. Goes all the way down to F sub m is now R mod F1 to Fm minus 1, mapping to R mod F1 to Fm minus 1, and this is injective as well. Okay, where again, this is just multiplication by Fm. So in other words, mod these things here, Fm is a non-zero divisor. Okay, so this is a regular R sequence. That's interesting. I like it. Okay, so at any rate, so here are two results about this, which we could prove here, but it would just take us a little further afield. It's pretty, they're pretty reasonable. So key fact number 1. Okay. So consider F1 to Fm with each Fi in R. Okay, if F1 to Fn, Fm is a regular R sequence, then the homology of this Kazul complex. Okay, now let's think about that for a second. What is the homology of it? You're taking kernel mod image at every step. So for instance, at R3, the kernel of del 1 is all the set of all syzygies on R3, and then you're modded out by the set of trivial syzygies. So H1 is going to be this interesting module, which is you get rid of the trivial ones and see what you have left, okay? And then you have the higher ones here as well. So this thing is one of two things, if it's a regular sequence. It's 0 if p is at least 1. Actually, if p equals 0, what is it always? So what is the homology at the rth step? It's the kernel, which is everything, mod the image, which is the ideal generated by the f's. So then this is equal to r mod the ideal generated by f1 to fm, if p equals 0. Okay. This is pretty good. This says, so i.e. K of f1 to fm is a free resolution of R mod f1 to fm if f1 to fm is a regular sequence. Is a regular R sequence. Okay. One thing else I want to say about this is that this is not really part of this, but I'll say key fact number 2 anyway. We're not going to prove this one either for now. This one is the following: is that f1 fm. Oh, actually, maybe I want it to be in a more. Actually, let's not do that yet. I wanted, that's probably in the homogeneous case. They're nasty. So regular sequences are really nice if the ring R is either local or nicely graded. Okay, but otherwise it can be the case that this can be a regular sequence, but you change the order of it and it's not a regular sequence. And so it's can be really annoying that way. But one typically uses this in the case where you have a nice ring. Okay. Now let's see. That's the definition. That's key fact number 1. Let's do key fact number 2, and then I'll state what I was just going to do. So first of all, if you take random polynomials, m random polynomials, they will be of the, let's say, homogeneous random polynomials, they will be a regular sequence. Okay, so that means that for almost any ideal you write down, this is the free resolution of it. And we saw that already with the quadrics. We took random ideals generated by quadric polynomials, and we were always getting, for 4, we were getting Betty numbers 1, 4, 6, 4, 1. And this is, if you looked at it closer, this would have been the free resolution of it. But here's key fact number 2. This one is the following. Oops. I'm just going to do it in the graded case. So if R is n graded, okay, not z graded. That means every element in R, the direct sum starts at 0 and goes on up. No negative degree things. If this is n graded, and the degree of each fi is greater than or equal to 1. Okay, and therefore this means that fi is homogeneous. Okay, if R is n graded and the degree is that, so I'm thinking of the polynomial ring here, and just usual degree, but it's slightly more general than that. Then the following are equivalent. 1, that f1 to fm is a regular sequence. R sequence. Typically, if you don't have a module here, which We are just doing it for R. Usually you might see it just written as regular sequence, not regular R sequence. But anyway, if it is a regular R sequence, that's condition number one. Condition number two is that we know that if it is a regular sequence, then all these other H's are zero. But in fact, all you have to do is check the first one. And of course, and then that's equivalent to HP of K of F1 to FM equaling 0 for all P greater than or equal to 1. Okay, and the 0th one is always R mod the generator, so that's like not a problem. So basically, if you only check the syzygies to see if they're trivial or not, you're not going to have any weirdness later on happen. So that's a pretty powerful thing. It's not true though if in general non-homogeneous rings and things like that, it can go bad. But since we never use it there, I'll let you. Maybe I should have an exercise up for finding an example where this fails in homogeneous land. Any questions on this so far? Yes.
Frankie, what should I be thinking interpretation?
I
I look at R mod the ideal generated by the FIs. I think, okay, that's the coordinate ring of the affine variety cut out by the FIs. Is that
Yeah, I'm actually really thinking of the coordinate ring. I'm thinking of R as like S, which is the polynomial ring. And then R, when you mod out by all of these things, you're getting the coordinate homogeneous coordinate ring one step down. R S mod F1, then S mod F1 and F2, and it's just cutting it down. That's a really good way to do any sort of induction kind of thing, except that if it's not a if it's a zero divisor, then it's very hard to get out control of it. But if it's not, if it's a non-zero divisor, then all of a sudden huge amounts of induction type of things will work. You just you say, well, okay, it goes down, and you have lots of proofs just work.
so I should be thinking projective varieties.
I would think in this case, the easiest, until you if you've seen it more, then maybe it's fine to think in lots of other cases. But for now, think projective varieties. S is graded by standardly by degree of xi is equal to 1, and then this is a bunch of homogeneous elements, and then you have the regular sequence. And it's called regular because regular element is another word for non-zero divisor. But it is true that I hate the use of the word regular. I always tell my undergrad classes that there's several words that are just normal, regular. Those are the two that come right to mind. But other words that are bad are obviously, trivially, but those are different kinds of bad words. Those are proof by intimidation words. Okay, so but in any case, this is now. How do you prove these things? I'm not going to prove them, but the way you prove it is that you write the Kazul complex on this guy in terms of the Kazul complex of one less guy. And you get a short exact sequence of complexes, and then you write the long exact sequence down, and then that gives you a relationship between them. And both these results just fall out in half a page once you have that machinery set up. Yep.
So you said that regular sequences are very common. Take random elements, we get a regular sequence.
So
So-
okay.
Random ideals are Kazul, or sorry.
So
Kazul complex of a random ideal is a resolution, pre-resolution.
mostly. Okay, so the question is so I don't know what the question is, but the statement at the moment was that if the F's are all, say it's homogeneous, everything's nice, and we have positive degree F's, and we take them randomly, then this will be a free resolution of this.
So in that situation, we got something sufficiently random. Do we get minimality of that
Yes.
resolution?
Yes, actually we do. Because, so the question is, do we get minimality of the resolution? And the idea is that if it were not minimal, basically one of these would have to be written in terms of the previous ones, but then it will be a zero divisor. So it will never be, it will be a minimal resolution. Yeah, that's a very vague thing. Well, in fact, over the rationals, what does random even mean, you know? You need a probability measure, doesn't really matter what it is. Yeah, it's really what you would say is generic. So in algebraic geometry, generic would be basically where all the coefficients just have transcendentally independent coefficients, and you just do it this way. But if you randomly choose things, all in practice, it will be this. Now, there's a problem though. What if I'm in 4 variables and I take 6 polynomials? Then this will not be a free resolution. But the reason is that this thing, each time you do this, what turns out to happen is you drop the dimension by 1. So R, whatever dimension it has, if this is a regular sequence, the next one down, R bar F1 has dimension 1 less than that. And you keep going, and if you finally hit dimension 0, well, then the next one can't possibly be. I mean, you're going to fail the fact that one of these is injective, basically.
Is that what we're calling two dots? Like this, pick a random set of elements, for this generate resolutions?
So the question is, does it take random elements? Does Macaulay 2 take random elements when it's computing free resolutions? No. There's an algorithm for it. And the algorithm we've already essentially seen, although I didn't really spell it out. You compute syzygies, you take a bunch of generators for it, and now you take the Grosvenor basis of that, keeping track of syzygies, and you just keep going back. There's ways of doing that faster than that, which would be an interesting little project also to write down. Yeah.
So you said that if the F's are a regular sequence, then the causal complex is a free resolution of R mod the ideal generated by the F's. But in your original,
This is over R. Right. So I mean, these are all free modules over R. So and this is just the R mod, the ideal is a module over that. It's also a ring, but
my question was in the definition of causal complex that you wrote down, the last term was R and not R mod the ideal.
no, that's exactly right. So do I still have it here? Not exactly, but this is a good example of it right here, right? So that's an R. So I'm computing the homology, H0 of it. So this thing is not exact as is. What is exact is exact at these 3 spots, but not at the first spot over here. But here, the kernel mod the image is R mod the F1, F2, F3. So if I change that 0 to be R mod F1, F2, F3, then this is an exact sequence. And that exactly says that this thing is a free resolution. So the free resolution is everything but the module. That's all the free parts in the exact sequence.
So when you take the homology of what's on the board there, you get R mod the ideal of the F's as the last non-zero.
So the question is, in this setting here, for instance, what happens? Suppose that, so if in this case here, F1, F2, F3 is a regular sequence, is a regular R sequence, then what do we get? Well, we get R mod F1, F2, F3. That is R, and then here we have R3. This is F1, F2, F3, which is also delta 1. This is always exact, right? So if I take it to the ideal, I take it mod that. So I have this thing it's going to give me a free resolution of this. All this stuff is the free resolution. And now here we get R3 and we get R again. And this is del 2 and this is del 3. This is the exact sequence, but this is the free resolution, this part here.
So on the board that you're pointing at,
Yes,
the first sequence is non-exact at that term.
exactly.
But then when you take homology of that, by adding an extra term of R mod the ideal, that becomes an exact sequence and is a free resolution of R mod the ideal.
That's right. So the question, the statement was that this is not exact here. This one, however, if we put in H0, this is H0, and we keep the rest of it the same, but now we take R mapping to that H0 because it's kernel mod image, which is R mod that. This is now exact here. It's certainly exact here because this is surjective. And so this is now an exact sequence. And the free resolution, it's just a notational thing. You might like to think of the whole thing as the free resolution, but really the free resolution is this part of it. Okay. Yes.
So when the Kazul complex is defined, isn't it usually done in terms of the exterior algebra, this sort of wedging in an element? And so therefore it's very clear that it's a complex.
Yes. And so the question is, isn't it really clear, much clearer to do it using the exterior algebra rather than
So, like,
this?
what you-
And I think that you're completely correct, that is a good way to do it.
you need to compare between the algebra and dual, so like you just sort of flip the degree for the exterior powers.
I don't understand that.
So when you have a basis.
When you have a
then
basis, okay, yeah,
so you could have, so that like your ease.
yeah,
That
Yeah.
defines parity between the.
absolutely. So you get a
exterior
pairing between wedge P of F and wedge of M minus P of F,
and therefore,
absolutely.
So now you have a mapping from the exterior in one dimension to its dual in the complementary.
Yeah, that's right. In
And
fact,
therefore it's, that's your. That dual sequence, but the way I've seen it done is just here's the exterior algebra, pick an element, wedge it, obviously it's a complex.
so here,
Zero.
yeah, so here's the one way to think about this is that you can do this as wedging with an element. And but the point being made is that that's actually from the dual of this. And that is true. But here's the thing is that in fact, this is a self-dual complex. So because of that dual, if I transpose it all and I just choose bases correctly, it will be exactly the same thing. So so it is true that doing it that way is very nice from a certain point of view, but I want you to also be thinking explicitly about it. At any rate, I don't have any good reason for why I left that out, except that I thought it would just be more complicated. But now that I'm explaining half of it all the time anyway, or you are, then it's
You know, it's clearly a complex, right? Because you have the exterior algebra, you take an element and wedge.
yes. So that is simple. This is pretty simple too, but maybe not as simple. Probably not as simple, but yeah, either way is fine. But there you have to do a little bit more work to just get it into this explicit form. That's all. And,
All excluding terms.
No, this all works in any characteristic. In part because I chose it so that EI wedge EI is 0. So that will not follow in characteristic
Well,
2,
for you,
but I'm setting that to be the case. You do have to be careful though, with finite characteristics, but not so much for these things. But that's for symmetric powers, you definitely have to worry about that. But we're not going to worry about that kind of thing. Any other questions? Okay.
So again, you think of R, your ring, the typical example as being S, the ring in n+1 variables, which is like the homogeneous coordinate
Right.
of Pn.
Yeah, so I'm thinking of R as being S of, which is the homogeneous coordinate ring in n+1 variables. It doesn't matter how many variables there are. It doesn't appear here, but yeah. Is that?
Yes, yeah.
Okay.
I'm just, my preferred, I care about interpretation because it helps me understand, and geometric interpretation is my favorite kind.
So key use of all this, or key situation, I should say. R is equal to S, which is K adjoint X0 to Xn. The degree of each Xi is 1 for all I. And the degree, and Fi is homogeneous of degree di, which is greater or equal to 1. You're not taking any, if it was degree 0, it's either 0 or a unit, and we don't want either of those cases. Okay, so this is the key use of it. But after a while, you might want to, when you are done, actually, this gives you a huge amount of, this is all projective geometry, essentially. And that's when we're going to be doing. I don't know how they did this, but I like it. Okay, one more thing I want to state about this. This is, I guess I'll do this as key fact number 3. Again, let's suppose that I'm going to do this in S, okay? So because that's what we're going to be mostly doing for. So let's let S equal k of x0 to xn. This is a lot more general though. And f1 to fm are in S, and the degree of fi is equal to d sub I is greater than or equal to 1. Okay. Then f1 to fm is an S sequence. So we have this induction kind of thing going on here. If and only if the codimension of the ideal f1 to fm is equal to m. Okay, which is actually quite cool. And basically, if it is a S sequence, you use this thing here with induction to show that the dimension drops by 1 at each step. Sorry, what? Yeah, is a regular S sequence. Thank you.
So that was called a complete intersection.
Yes. So the definition is that if, in this case, if the codimension of f1 to fm is equal to m, we call x, which is the zero set of those guys, f1 to fm, a complete intersection. I should actually say this differently. Complete intersection. This is not quite accurate. This is if the ideal of x is equal to f1 to fm. By the way, if it's not equal, but it is the same zero set, then it's what's called actually, what is it called? It's called a I'm blanking on the name, but it's a big important question as to whether varieties are always complete intersections if you only consider it up to radical. So, and but anyway, so this would then therefore this is going to be if and only if f1 to fm is a complete intersection. Okay. So, but this is the definition of complete intersection. Okay, so I don't like the way I phrased this, but let me get rid of these parentheses here. So as long as the ideal is generated by m elements, then it's a complete intersection. Okay, these are all once you have this way of linking a Cazorla complex with smaller Cazorla complexes, then all of these things become quite easy to prove, except here you need to be able to, you need to have some basics about the relationship of these sequences with dimension. But if it is a non-zero divisor, the dimension drops. But maybe it drops by more than 1. But by the Krull's principal ideal theorem, it can't drop more than 1. So then you have there's some other commutative algebra stuff that you have to come to grips with in order to really prove it. That's one of the things I like about Shafariewicz's book on algebraic geometry he, instead of like just saying, oh, well, Quill's principal ideal theorem, or maybe if you want Quill's, Hauptideal Satz, whatever instead of doing that, he just rolls his sleeves up and just proves it right off the bat. So it's very empowering. Okay, so this is the Cazorla complex. It comes out a huge amount. The geometric thing is that it's a complete intersection. This regular S sequence basically means that any homological algebra with it, because once you have these things, you have all sorts of short exact sequences and things like that. So you can relate X and pores and things like this. It all works beautifully. So in some ways, if your ideal is generated by these things, the geometry matches the homological algebra. If it isn't, then it doesn't actually match it. It's a little off. So, and that's in fact where cohomology is often coming in. So, questions? Say it again.
Yes.
So I'm saying that geometrically we have the notion of a complete intersection. Okay, that's a very nice situation. The dimension drops by 1 each time. Everything's great. We also have the situation where it's a regular sequence. Now, if you have a regular sequence, notice what you do is you get a whole lot of short exact sequences. This is injective, so it's 0 goes to this thing, goes to this thing, goes to R mod this thing with the FM. Okay, and so now you have a short exact sequence, and you can use Hilbert polynomials. You can do all sorts of things to relate all of these things together, and that will actually probably allow you to prove all of this stuff pretty easily too. So, but the point is, what I just didn't say there is that this way is sort of like a homological algebra way of thinking, where you have a bunch of short exact sequences and things like that. And then this is the geometric way of thinking. And in the case when you have a regular sequence or a complete intersection, those things match up very nicely. It's when you have like even the twisted cubic has 3 generators and it's codimension 2. That's not 1. Then all of a sudden it doesn't quite match up as nicely. That one still is pretty good, but it can get worse. I think what I would like to do is take a break and then do more of the cohomology stuff. And then in the last hour, we'll do sort of playing around with some of the stuff. Because I would like to get to some of the theorems on the cohomology and say what that all is. So anyway, let's take a 10-minute break. Is that good? Okay, we'll do 10 minutes. It's 11:08 now. So 11:18, we'll start back here. Yeah, right. Yeah, no, it sounds pretty cool.
Yeah, nothing is new. It's all totally new.
Okay. So everyone back mostly? Yeah, right. So anyway, okay. So what I want to do now is do 2 things, basically do 2 things, and then also define, state some of the facts of Serre that we can use in the project part of this thing. But first, I wanted to go back to the Czech complex, revisit it, because it is true that I should have given you the maps when we did that. So we're going to let S equal K of x0 to xn. And here's the Czech complex. C of S, say, is, and it's going to be 0. This one goes, this is a, like a the numbers go up. And it can go to, it's in Pn, so the top one is n here, not n plus 1, even though that's the number of variables. And we defined this last time, but where Cp is equal to the direct sum over all I0 less than I1 less than ... less than IP between n and 0. So again, it's like an exterior power, which it is in some ways. Okay, but instead of just taking we have a whole ring here, And basically, we just invert by all of the variables here like this. So xi0 inverse. I could take the product because it would be the same thing, but I'm thinking of this as all of these guys I've inverted. So this is a graded, infinitely generated graded S module, which is also a ring. But the fact that it's infinitely generated over, actually infinitely generated over K or S is what's going on here. But there's that. And what's the differential? So the differential, actually, let's write down where they go from. Again, we always name them starting, so this will be del 0, del 1, del 2, del n minus 1. And we have to say what those are. By the way, I often use dels for complexes as maps. Here, the index is on the upper side since it's going up in numbers, and if it's lower, it's when it's going down. But that's just a convention. No one really. That's just. There's reasons for it, but it doesn't. They're not super great reasons necessarily. Okay, the differential is as follows. So I need del p from CP into CP plus 1. So how do I do this? I have to take an element of this thing and say where it goes. I could take an element in one of these things and say where it goes, but it's just as easy in this particular setting to do it as follows. So let's suppose the differential is given by the following. First, before we do that, so we suppose omega is in C of P. Okay, so it's in here. What does omega look like? It's got an element in lots of different components. So I'm going to say it's a W alpha. Omega is W of alpha over all possible choices of alpha, where alpha here is equal to I0 to IP, just like here. Okay, so it's really just a bunch of elements. Each one of these things is a polynomial, or is a rational function rather. It's a polynomial divided by some power of those variables, is the way to think about it. But anyway, that's what you have here. Okay, and now what is the differential del p of this omega? Well, in order to say what that is, I have to tell you what the component is at the next step up in here. So I have to tell you what this is at some index set I0 to IP plus 1. Okay, that's what these guys are. So the elements in here look the same as this, except now the alphas have p one extra. By the way, notice this is going 0 to p, so it's shifted in by degree by 1 from the Cazorla complex in an annoyingly confusing, and easy to screw up manner. But the reason it's done this way, well, it has to be done this way because if we change the indexing, then we'll get screwed up later on if we do it that way. But anyway, it doesn't matter one way or the other. We have this. So this thing here is going to be an element in here, and so I have to tell you what it is at this index. It's going to be an element of this thing, except now where we have these guys are all these variables have all been inverted. But this is going to be equal. Again, it's the same kind of deal. I don't know of a simpler like exterior algebra way to write this one, but there probably is. J equals 0 to P plus 1. So this is this index set here. And what is it? It's minus 1 to the J. Again, I chose it so the first one is positive. And then this is omega. But now I need to give, all I know about omega is that it has these things. But so I just removed the jth one of these things. So this is going to be at the point I0, IJ with a hat on it to IP. And this is remove this one. It is extremely similar to the Cazorla map. In fact, it's even much more than similar to it. because if I look at various degree parts of this, I'm going to get all sorts of Cazul complexes. But in any case, this is this. And the exercise here, which is almost identical to the other one, except that the notation's a little different, is that show that C of S is a complex. And then if you recall, so last time we had defined, so let's let M be a graded S module. Let's suppose it's finitely generated, but that's just for, there are ways around that if you really care. But let this be a graded S module, and then we define HI of the sheaf M tilde. To be, by definition, is I take this complex, this guy over here, and I replace every copy of S by M. And if you think about it, when I replace it by M, okay, and I'm still inverting by those variables, it's going to be a module over this thing. So we've got lots of modules over lots of different things floating around, but this is still tensor over S of M. This is a nice graded complex. So so this thing here, I'm going to take I'm going to take HI of this. This is a complex, so this is kernel mod image of that complex for that. And then I'm taking the degree 0 part. So I'm taking degree 0 in every single component, everything. This is a graded, so note, C of S tensor over S of M is a complex of graded S modules. Not finitely generated S modules, but graded. And so I can take each degree D part of this. So in some ways, so C of S, direct sum over S of M, is in some ways equal to C of S, direct sum over S of M in degree D. Oops, I didn't leave myself enough room. Direct sum over all D and Z. Is it all? Are negative values here allowed? You know, most of them are going to be 0, but you know, anyway, you can still do this. Okay, so if you think of this as a so this thing here, what kind of? Let's just be let's be kind of let's do a type check here. See this thing here, C of S tensor M, and then I take this thing here where I take sub D. What kind of object is that? So let's actually write this down. So note this, and so where C of S, not where, but so we have that C of S tensor M in degree D. I should have written down degree D maybe, but this is but what is it? What kind of object is this? If I take a sub degree D, it is a complex, okay? Is it a complex of S modules, of K vector spaces? You know, what is it? It is of abelian groups, that's for sure, but it's also of K vector spaces here. Okay, so this is a complex of K vector spaces. Where K is the base field that we started with. Actually, if we did over the integers, then it would be just a complex of abelian groups. Okay, so but in any case, we're only going to define it here for the time being. But these are not finitely generated, okay, at all. So this is just some infinitely generated. You know, every term. Well, it stops at position n, but basically it's all that. Questions or comments? No? Okay. So definition is this. This is the first definition. And then if you note from this definition, if I take HI, remember if I take M of D and I sheafify that, I can do that as well. That is equal to HI of the C of S tensor M. But now in degree D. Okay, I think I've got the D and not negative D correct. Okay, I have 50% chance of getting the sign of it correct, but I think I have this one right. And then we also define HI lower star of M tilde. By definition, this is in fact equal to HI of the whole thing, C of S tensor M. You're all tensor over S. Okay, which is equal to the direct sum over all D in the integers. Most of these will generally be 0 of HI of M tilde of D. So if you want just one of them, you take that current part. If you want a different shifting, you have two options. One is you just change that and take the degree 0 part, or you just take the degree part of the original one here. And if you really want all of them, this is going to be this is an S module. It's an S module because this is a complex of S modules. So when I take kernel mod image, it still is. Okay, so these are the definitions that we would maybe like to have here. Now, oftentimes in algebraic geometry, you just care about one of them at a time. In commutative algebra, you're much more likely to care about the whole module and see what it's like. Okay. Now, if you recall from last time, we also had the following. So we had so from last time, we had that the computation of HI of O of Pn twisted by D was equal to one of several things. One was it is equal to the dimension of SD if of I is equal to 0. Okay, so number of polynomials. So it's a basis of all the polynomials of degree D or of the monomials of degree D. It's 0 if I is between 1 and n minus 1. And then it's the dimension of S in degree, actually, yeah, let's see, degree of S in degree minus D minus n minus 1 if I is equal to n. Okay.
Question.
Yes.
Use the phrase twisted by D. Can you shift it by D? What do you mean by twisted by D?
So the standard name for it in algebraic geometry is twist. But for us, algebraically, it's just a shift of degree. Okay. There is a twist going on. It's in vector bundles. If I have two open part in algebraic topology or whatever, or in topology, if I have a vector bundle, I have open set here and I have an open set here, and I have the transition maps between them. If I shift it like this, then I'm actually changing the transition maps, and so I'm sort of twisting the. I have never really completely seen it that way, but that's the reason why it's this is shift twist. It's all that. Okay, now this thing here is a little weird. And in fact, if you see it, this goes off infinitely far negative. So note that Hn of OPn star is not finitely generated. Well, if it's finitely generated, it has to have some lowest degree generator for it, since it's grade A, right? And so, but this one is non-negative, is non-zero in all small degrees. So this thing you're kind of out of luck. Okay. But the question is, what is this? This object has a nice way of doing it. And so now we're going to talk about the graded K-dual. So the idea is the following, and on the Jupyter notebook, I have one sort of example where you can sort of start to see this right away. But if M, suppose, okay, here, let me get myself some room here. So if M is equal to a graded S module with Hilbert function. So remember, that's just the dimension of M sub D in every degree, right? So if I look at D here and I have degree 0, 1, 2, 3, 4, etc., and also -1, -2, if it's finally generated, it's you're going to be 0 after a certain point going negative. So let's call these numbers D0, D1, D2, etc., and D-1, D-2, so on. Okay, so this is the dimension of M in degree D. That's D. Okay. The graded K dual is going to be made from M, and it's going to flip this around. So, so we will define the graded K dual M check so that such that the Hilbert function, so if I have D here and I have dimension of M hat sub D, okay, and here's 0, 1, 2, etc., and here's -1, -2, etc., then this is going to be D0 still, but now it's going to be D-1, D-2, and so on, and D1, D2, and so on. Okay? That's what we're going to define. And it's going to be easy to define whether we understand it yet or not is a different issue, but it's kind of cool. So notice, by the way, that if this is if this is a finally generated module that is finite, okay, so let's do an example. Actually, do I want to do an example yet? I want to define it, and then we'll do a couple examples. So definition: if M is equal to the direct sum of M sub D for D and Z is a graded S module with each M sub D finite dimensional over K. Okay. This is what we've always seen. The only time that I mean, if I took an infinite number of copies of S, this would not happen. But if any time we have finite generation, this would happen. But it would happen in more cases than that. Okay, so anyway, so if this is the case, we're going to define the graded S module M check by the following. Well, it's graded, so it's going to be equal to the direct sum over M dual sub D for D and Z. Now I just have to tell you what each of these things are, and maybe I also have to tell you what the module structure is, because this is just given to me as a bunch of vector spaces. Okay. So M check sub D by definition is going to be M sub minus D prime. This prime here is the K vector space dual. Okay. So what's happening here? I'm shifting the degrees and I'm taking prime. Actually, already that gives us these properties. Whether as soon as I can actually make such a thing out of this, it will give me the properties, because the degree D part of this will be the degree negative D part of this, because vector spaces and their duals have the same dimension. Okay. And now we have to understand what the matrix, what the multiplication map is, but that's actually pretty natural. And this has a natural So if this M tilt, let me actually put it up here. Are we, yeah, okay, good, thank you. You guys are more on the ball than I am with the cameras. Okay, then M check has a natural structure as an S module. So for instance, what do I have to do? I have to take an element of degree D here, right? And take an element of degree 1 in the polynomial ring. And I better have a map that goes from here to here. These are vector spaces now, so this is over K. That this had better map to the next higher degree in that M, which is M hat in degree D plus 1. Okay, so this is the multiplication map, really. Okay, so we have to say where this comes from. Well, if you think about it, what is this map? So this is one way to think about this. This is, first of all, this is M prime in degree negative D. And then this is going to be M prime in degree negative D minus 1. So what is the map? So if I take an element here, remember this thing makes it a function. So if I take an M, which is really a function from M minus D to K, and I tensor it with some variable, say X, or any linear polynomial, what does this map to? Well, now it has to be a function from minus D minus 1. So it has to be a map that gives M prime, and what is it going to go to? So M prime is in M, this is in M minus D minus 1. These are, by the way, the kinds of natural things that I remember always seeing and could never actually grok in real time, okay? So, but in any case, so this thing is mapping to a function from here to K. So I need an element of the field here. What is it? Well, I don't know what to do here, but if I take M prime times X, that is an element in one higher degree than this, which is in M minus D, right? But that's this. But now M takes elements of degree D minus D and gives me elements of the field out of it because it's a element in the dual. So I just apply M to that. So that's my natural map. When we do some computer stuff, maybe I'll show you how to do this, but basically you need to check that this thing is a graded S module. And actually, almost by definition, if I take its dual, that's back to M. So it is sort of a dual thing, right? So we have that. So here's an example. Suppose M is equal to K of xy. Here S is equal to K of xy. Modulo x squared, xy, and y squared. Okay. So what is the Hilbert function of this? So here's D, and here's the dimension of M sub D. Okay, nothing in negative degrees, but so 0, 1, 2, and so on. In degree 0, the only element is 1. In degree 1, the only elements are both linears survive as elements, so we get 2. And in degree 2, what's left? Nothing. This is equal to 0 in degree 2 and anything higher. Okay, so the Hilbert function of this is just a simple 1, 2 in this case. And now what is M dual? So it has to have two so actually we can write down then. I should have done this all in one thing. This is non-zero in degree -1, and then degree 0, and then 1, etc. And this is the dimension of M dual D. This is going to be 2, so it's going to be a 2 generated ideal, at least, and then a 1 here. And probably that one will not be a minimal generator, but you never know. And then zeros after that. So it just flips it around, and it changes the. So what is this module? Yes.
wouldn't be.
I guess if you define it the way I did it, it's the fact is that since they're graded finite dimensional vector spaces, there's a natural isomorphism of M and its double dual. I know. So this is a natural isomorphism. Okay. But if you think of it the way we defined it, yeah, I guess that's right. Assuming, yeah, it's a natural isomorphism. Okay, what is this module? So here we have two elements, and these are going to be the duals to those two things. So if you think about it, and maybe I'll let you think about it, even in break. I'm going to write it over here. So M dual, it turns out, is S2, both in degree with a -1 in it. That's two generators. Oops, wait a second, that's not right. They're in degree -1. So this is a +1 here. Okay. And modulo something. And it turns out that what it is in this case is y0, x minus y, and 0x. So when I say mod this, mod the image of this. So these are S2, both generators have degree -1. And y times that one, the first generator is 0, x times the last generator is 0, and x times the first and minus y times the second are 0, add to 0. And there has to be something along these lines just because of the fact that it's an S module sort of thing. So it's worth thinking about this one. So exercise is a good one to do in break even, is show this explicitly. But here's a fun fact. If M sub D is equal to 0 for all D sufficiently large and all D sufficiently small, okay? So in other words, this is one of those examples. This is 0 from 2 on up and 0 from -1 on down. Then we can write down what this is. Then M dual is not colon equals, is equal to x. So this is S here is k of x0 to xn. M dual is equal to x of n plus 1 of S mod of sorry. I'm thinking of it in terms of ideals. I was going to write S mod I, but we have an M here. So this is M S. Now there's a shift in degree, -n minus 1. And this thing is equal to this. Okay. This is something, by the way, you have enough to prove right now. That this is at least that the dimensions match up for this. And the reason you have that is if M is like this, then it's finite dimensional, and therefore we know that the free resolution goes all the way to the end. Actually, do we know that? I think we know that. But anyway, so that we can actually, from a free resolution of M, we get a free resolution of this whole thing here. Maybe I'll think. I have some of the information on this in the in one of the Jupyter notebooks, but not completely, maybe as much as is necessary. Anyway, this is kind of cool fact that this xn plus 1 is this duality thing, at least if you have finite dimensional things like this. Or actually, it isn't even necessarily finite dimensional. This is true if this is equal to 0 for all d less than or equal to 0. No, I'm getting confused. So for all d great sufficiently large, we'll have to say what it can mean, because it's not going to be true if M is not of this form. Okay. That's it. This is example one. Oops. Here's another example. If I take S is equal to K of x0 to xn again, what is S dual? Well, that is kind of this thing here, right? This thing is what it's except for the minus n minus one. This is going to be sort of like the dual of it. So S dual is going to have its largest degree generator in degree 0, and it's going to get larger and larger as you go negative. So this thing here, it turns out, or maybe I should write this as an exercise because it's a good exercise, that this thing is equal to K adjoin 1 over x0, or 1 over xn. And the multiplication, if I have a 1 over x to the alpha, so that's an element of this module. And if I multiply this by x to the beta, say, okay, this is in S and this is in S dual. So this has to equal an element in S dual. That's what the graded the module structure has. So what is this element? It's one of two things. It's 1 over x to the alpha minus beta, sort of like differentiation by x to the beta. This is if x to the alpha, if x to the beta divides x to the alpha, so that alpha minus beta is an actual monomial, and it's 0 otherwise. Okay, if you haven't done any commutative algebra much, you won't notice this, but this S tilde, this thing is equal to E of K, which is the injective envelope of K in S, or with respect as an S model. Okay, now this is kind of okay, so this is fine. This thing is infinitely generated, but it's kind of very mildly infinitely generated because I can write down what's going on. Okay, this E of K is an injective module. All injective modules, other than this one, are messy and nasty, essentially. Okay, but this one here is infinitely generated, true, as pretty much all of them are for this polynomial ring. But most of them are uncountably generated. But this one has a nice fact about it. But the exercise is really just to prove that this is the case. Okay, and now where are we here? So now I want to state some of the theorems. I think I'm just going to do the local duality ones for the moment. So the theorems of Serre in his fact paper in 1955. It's really hard to believe. I mean, as I keep saying, this is a really, I think, a really good paper. There's lots of stuff in it that that goes above and beyond, say, even what's done in Hartshorne and stuff like that. So so here is the there's a couple of things that I might like to say, but not right at the moment. So the first thing is HI. So again, let's let M equal a finally generated S module. Okay, and now we can take its cohomology, HI of M tilde. This is not colon equals, this is equal to x of n minus I sub s of m comma s dual in degree negative n minus 1 for I greater than or equal to 1. Okay, so x, or I hope m comma s, these are the friendly x things. The dual is this slightly less friendly but pretty nice thing. that at least you know what all the dimensions are without any more computation. And then in this particular degree, that gives you this vector space HI of M tilde. Okay. And B, we'll just do it without the module structure at the moment. Actually, no, let's. So the other thing that is true is that HI lower star of M tilde is X of n minus I of M comma S. This minus n minus 1, though, needs to be put in as a shift now because we're actually getting a whole module. And then it's the dual of this guy. Okay. Again, this is for I greater or equal to 1. Wait a second. H equals 0, by the way. I equals 0 are the global sections of this. That's the one that is whenever you're dealing with sheaves, that is the one that you're most interested in almost all the time. So here we don't say anything about it yet, but we do have the following. But before I state it, let's just think about it for a second. This is computing using Czech cohomology. This is done using a free resolution of M. Okay. And somehow that Czech cohomology and this X of this thing are the same. And that's just rolling up your sleeves, going into the homological algebra and showing that those two things are the same is essentially all it is. Okay. So but it's actually a pretty good comment. And then but now what happens at I equals 0? Then we get the following. We always have a map from M into this H0 lower star of M tilde. If you think about what this is just the standard map where I take an element of M and it's going to be the direct sum of the same element, but inverted by there's a natural map from here to here. But it turns out that we can actually identify what the kernel and the image are. The kernel, oops, I didn't really give myself quite enough room here, is xn plus 1 of S of M comma S twisted by minus n minus 1. Dual. Okay. So forget the duals for the moment. But basically what this is saying is that for any degree D, I have MD mapping to this thing, and the kernel of it is going to be something that I can compute pretty readily. Okay, it's an X. I have to figure out what degree it is. Okay, that's true. That's annoying, but we have that. And then on the other side, the question is, what new sections do you get? So this is telling you when two sections give you the same element of global sections of the sheaf, is if that's there. And what you get is that you have xn. Notice that this one here, by the way, I equals 1 is n minus 1. So we're in n plus 1 variables. So the largest thing that we can ever see is up to degree is xn plus 1. And here we get xn plus 1 and xn. This is m comma s twisted by minus n minus 1 over s dual goes to 0. Okay. So in particular, that gives us if the projective, so two things in particular. I could say that m sub d is equal to this thing sub d. In other words, I already have it computed if this and this are 0 in that degree. Okay. But another time that you can say it is if the projective dimension over S of M is less than or equal to n minus 1. In other words, that means these two x are 0. Then, in fact, we have M, this natural map from M to H0 lower star of M tilde is an isomorphism. So somehow, if you look at the free resolution, remember M here, I'm oftentimes thinking of S mod I, but I might also be thinking of other modules like the sheaf of one forms or something like that. But basically, if I have a short enough free resolution of that thing, then I get H0 on the nose with no further computation. And all the intermediate X are up to dual, but you kind of ignore the dual part. are essentially are all the intermediate cohomology. So, or all the higher cohomologies rather, H1 all the way up. So, and this turns out to be pretty good way of actually computing these things. There's a better way that we're going to learn in a few classes from now, which is the Bernstein-Gelfand method. But nonetheless, this is a really good way. It really links sheaf cohomology, these what I think friendly X that we've got that are very computable, and the commutative algebra that comes from knowing a bunch of stuff about this. So here's one of the things that would be good to do during the next thing is use this to prove a couple of theorems of Serre. Okay, and that you don't have to do Macaulay 2 for it at all, but it's a useful thing. So let me write down what those are. There are two theorems of Serre that are really they're in second chapter of Hartshorne, kind of. But here are two theorems of Serre, which are not necessarily originally proved this way, but should have been, I think, and maybe they were. Actually, they probably were. Now, what are they? Oops, I don't have them written here. So the first one, actually, how do I want to say this? You have it in the I don't know where I have it. So the first theorem is that HI of OX of D equals 0 for all I greater than or equal to 1 and all D sufficiently large. Okay, so this is one of the things. The higher cohomologies, not I equals 0, but all the other ones eventually die out. Okay, and the second one is that for all D sufficiently large, OX of D is what's called I'm just going to write it in quotes here and I'll say what it means, generated by global sections. Which basically means well, this is a weird way to write this, but it's the same thing. So that if that M in degree D is equal or isomorphic to H0 of M tilde of D, these are both vector spaces. This is that these are equal for D sufficiently large. Okay. And it follows directly from this kind of stuff, from everything we've done today. But it's not hard, but it takes an unraveling, which is actually a good use, a good thing to
Mike,
do.
sorry, what's X in number 1?
So X here is contained in Pn is a projective variety. And actually I said this badly. Actually, I did it for O of X, and really what this is S mod I in degree D is equal to H0 of O of X in degree D for D sufficiently large. Let's get rid of that because there's no M in sight. I can also say something about what happens for all sheaves, which is really the way I should have stated it. 1 prime is that if M is equal to graded S module, and the usual properties finitely generated, say, then HI of M tilde in degree D equals 0 for all D sufficiently large. Okay, this is just a special case where O of X is S mod I tilde. and that's 2 prime, is the same thing as what I just basically said before. For D sufficiently large, M sub D is isomorphic as K vector spaces to H0 of M tilde sub D. It doesn't matter where the tilde is before or after, it's by definition anyway. And this is for D greater, large enough, we always get all the sections that we started with. So, so these are sort of the key theorems of Serre that get used all over the place in the whole theory, and they follow directly from the stuff here. Okay, what else do I want to say about that? I was going to do, I thought I'd do one example, the twisted cubic, and just say what this actually looks like. So you might need to change the camera. So let's do an example of the twisted cubic and just see what it says. So the twisted cubic. So remember, one way to think about this is that we have the map of P1 maps to a curve C inside of P3. And if the coordinates here are ST and the coordinates here are x0, x1, x2, x3, the map is I take an element ST, which you might write as S colon T if you've ever done this sort of thing before. And then you just map that to S cubed, S squared T, ST squared, and T cubed in P3. So again, you might want to put colons in there if you like that kind of thing. And then the ideal of the, and C is equal to the image. And the ideal of C was equal to the 2 by 2 minors. So remember, this is x0, x1, x2, and x3. So we have to find all polynomials that vanish on this, which is a Gribner basis thing. And this is x0, x1, x2, x1, x2, and x3. And this I2 means the 2 by 2 minor, like we've had before. Okay, so this is contained inside of S, which is K of x0 to x3. And now we would like the cohomology of, so we would like O of C, HI of O of C equals. Now in reality, everything is, this C is actually isomorphic to P1. So this is going to be HI of O of P1, but we want to make sure that it matches with what we think of as far as that goes. So how does this work? So what I want to do is I want to compute the cohomology using the theorems of Serre. So how do I do that? Well, the theorem of Serre basically says, here we're going to let M be S mod I sub C. And then we're going to we want to compute all these X, which means we have to compute a free resolution of it first, and then actually just see what it says. Okay, so let M be that, and next compute a free resolution. We've already done this a number of times, but this is what it looks like. 0 goes to S mod IC. S, there were 3 quadratic generators. That's S to minus 2, 3. And then if you remember, there was also minus 3 to the 2 here. And this was a 3 by 2 matrix given by x0, x1, x2, x1, x2, x3. What was that? Oh, oh, okay. So any case, so we have this, and then these are the 3 2 by 2 minors right here. Okay. So now, what are the various x's here? So x0 is computed here, x1, x2, x3, and x4. Okay. So note that I, oops, sorry. xi of S mod IC into S, we might want to do the shift here. We can, this shift also works if we put it right outside, but still inside the check. So if I take this thing, this is equal to 0 if what is true? Which cases is this equal to 0? Well, this is at 0, 1, 2. So anything higher than 2, it's 0. So I equals 3 and 4, and actually higher as well. It's all 0. But we're in 4 variables total, so it will never go past that in any case. So that's equal to 0 if I is equal to 3 and 4. X2 of S mod I sub C comma S is not equal to 0. That's computed here. That's going to equal S, when we dualize it, this is S3, 2 copies, mod the transpose, the image of the transpose of that. Image of X0, X1, X2, X1, X2, X3. Okay. What about X1 and X0? How about computed, 0 and 1? How about those two? Well, 0 is the kernel of everything. Oh no, but it's hummed. Sorry, we've transposed it. So it's really the map from here to here for the x. And so the x 0 and 1, actually for 0 and 1, they're both 0. And that was because, remember, they were 0 lower than the codimension. So I should write down somewhere, note, the codimension of I sub c is equal to 2. It's a curve inside of projective 3 space. So the 0, 1 actually follows directly from that, and the 3 and 4 follow because of the format of this thing here. So what does that tell us? So what does Sayre say? Well, we have various h's here, right? So which ones are non-zero, which ones are 0? Actually, maybe I should leave this as a good exercise to finish, to do all there. But where do we want to find? I want to know what hi of O sub O of C is equal to what? Okay, I might actually be interested in hi of O of C by any twist, but certainly these are the first things that are important. So maybe I'll leave this. This is a good thing to play around with as a first example also. There's so are there any questions at the moment? Does this make any sense? Or is this too so these things here look weird, but what's kind of cool is that these cohomologies are nothing else other than an x with this change in that you have to flip things upside down. That, which is annoying, but nonetheless, sorry, this one here is actually the k vector space dual of this vector space, because the dual yeah, it's the same thing, but basically that's what that is. We need the dual if we want the whole module structure, but otherwise we just have this as a k vector space dual. And if I wanted to write this down for every degree, I could also do it as just k vector space duals and not worry about these graded k duals. Do you like the graded k dual, or do you not like it, or you're not comfortable? Are you comfortable with it or not comfortable? You're not comfortable with it yet, but it's actually not so bad. It's just sort of flipping things upside down somehow, and taking vector space duals of every part. So that part you should hopefully not worry about. But what it's really showing is that if you know the free resolution, you have a lot of control over the cohomology, which is actually really cool. we don't know how to, we don't know why we care yet about this. And the thing I was going to do, which we didn't get to today, is the Hodge diamond. Again, I'm not sure if I want to continue this again into next week, but I'll think about it. But I think we need an example of that kind of stuff. So I think it's a good thing to do.
What is the topology of this twist?
I mean, it's just a P1. It's isomorphic to P1. So it's just a projective line over the complexes, which is a S2, I guess. So okay. So H2 of this is not going to be non-zero. No, this one is not, it depends which one you're talking about. If you're talking about the topological ones, we haven't actually said where the topological ones come from yet, by the way. There is a relation, and that's not in the Hodge diamond stuff that we will talk about maybe if we continue it next week. So what?
The middle group.
Here?
Well, only the middle. Isn't that? Oh, actually. Forget it.
Yeah, no, it's not the same. I mean, they're related, as you say, but it's definitely not the same. This is not singular cohomology. In fact, to tell you the truth, I do not know a good way to really compute singular cohomology of an algebraic variety, other than using the Hodge theory, which is part of the Hodge diamond. And that only gives it to us without the torsion in it. So if you have a torsion part, it's very hard to compute that, as far as I know. Maybe someone in algebraic topology could say, "Oh no, that's really trivial to compute," but I don't know how to do it. I know how to do it in some cases, but he said it was not trivial. Okay, well that's good to hear. If Attia said it wasn't trivial, that's 50 years have passed. That's right. There are instances where you can calculate it. For instance, if I take a toric variety and I take a hypersurface that happens to be a Calabi-Yau threefold in there, then it turns out you can use the combinatorics from toric varieties to compute it. And you can use it to compute all this stuff too. So, this is all done on projective space, what we're doing now, but these things here do not quite generalize nicely to toric varieties. It would be really nice to understand what the generalization is. I mean, this is not quite it. There are other ways of computing those things, but they're a little more time consuming. So it would be nice to have that. Anyway, so if anyone would like some of these things, I have 3 handouts for you. The week 6 questions. I might even have enough here for some. I have only a handful of the Hodge diamond, which we didn't get to. Maybe I'll keep that for next time. And but this is the Cazul complex and check complex thing, which is not quite complete. I haven't written this stuff into it yet. These are at that one website I put out. This is in my GitHub repository that I'm starting to put all these things in. I've got a bunch. Were you around when I was talking about that? I have a bunch of Jupyter notebooks that I've started up, and these are them. These are the PDFs of them. Here you can. They're not stapled or anything. See, and you can sort of take a look at that. These are just PDFs of it. If you want, you can go and get the actual Jupyter notebook, but I think right at the moment, it's probably just as easy to use this and type it into Macaulay too, if you want to do any of that stuff. But it has some of the definitions we did in class and so on. But I recommend as I first run taking these theorems here, which are on the board, and at least doing these 2 examples to sort of cement what has been said here. And then you can look at some of the exercises in there that are not so bad. Oops, did I, what? I cleared the cells. I had to clear the cells before I checked it in. I didn't have to, because otherwise it's a huge mess at the moment. Because the cells are quite big, it doesn't do it correctly. So, yeah. The Jupyter cells are also cleared at the moment. But this is basically to get you so you can type it in, directly. Or if you have Jupyter, then you can go grab the Jupyter notebook. Yeah, there's some benefit to actually having to type it in as well, especially since there's not that much to type in. But there is a benefit to being able to just go through it too, and then you can get that from the GitHub repository, which is public. One thing I was talking to people about before, you can keep working and ignore me, but is that one great thing as a project would be to create or improve the Jupyter notebooks we have for different computations that you might want to do in any of these fields. For instance, in simplicial complexes, and that would be a good such notebook also. The math in it is a little annoying sometimes, but I mean, as far as getting the tech just right, but in fact, I haven't quite figured that all out yet. Yeah.
Well, okay, yeah, so I was gonna say, like, I noticed, I guess,
Actually, before you do it, let me just check. Are there any questions from people online? Okay, I'm going to take off my well, maybe I should leave it on.
I was just looking at the column 2 textual output from the Macaulay site.
Yep.
And it looked like you had predefined some LaTeX commands like /zz/.
We have.
Yeah, so
There's a list of them somewhere, but I don't know where. Which is nice, but it doesn't work in Jupyter Notebook. So
like to add
add stuff for any page. Oh, actually, I'd be interested in hearing that. I had a rough time. I was trying to change, put in a better title and, and something about our class. What?
Show me.
Yeah, sure. Yeah, maybe I will take this off for the moment though, because I'll just annoy people. Put it on if we want to talk.